The following program is brought to you by Caltech.
Hi, my name is Nick Parziali. I'm the other co-lead for the 2013 Caltech Space Challenge. I'm a fifth-year PhD student here at Caltech. While these folks are getting set up, a story about how we chose the order of the teams. Jason and I initially selected a coin flip, or initially suggested a coin flip, but the folks in the Explorer room said, no, this is a space mission design competition. We should do something like a random number generator. And Jason and I looked at each other and we go, that's too nerdy. So we come up with a compromise and we do a coin flip with something nerdy. We took a diaphragm from the T5 reflected shock tunnel that sits atop the roof. We wrote Explorer on one side, Voyager on the other, and we flipped that. So are you ready to go?
Good to go.
All right, with that, join me in welcoming Team Voyager.
All right, so as you heard, we are Team Voyager, and this is going to be a presentation on Expedition ASOF and going through our mission architecture for it. So first of all, I'd like to start with our mission statement, and we as students were selected to design a mission to land humans on a Martian moon, either Phobos or Deimos, and return them safely to the Earth along with a sample, with a launch date no later than January 1st, 2041. All right, so our motivation behind this is pretty straightforward. It's motivation that advances all space exploration. So to start with, we have advancing human exploration, and this is one of our primary science objectives. It is mainly focusing on long distances and time conjoined together to study the effects on astronauts and humans. This is something that's not really available in our current space environment. With the ISS, we can do long durations, but the extended distance away from home is something we cannot do. And then we get into the science, primarily planetary science. We want to focus on composition, age, and origin. And one of the things we want to focus on is there water on Phobos? It can be quite beneficial if we find it there. Then we want to go into the relation to the Mars system as a whole. If we can study these planetary bodies on Mars, we can further understand how planetary bodies elsewhere work, and then mainly the Martian planetary system. We also want to study biological sciences, and this includes physiological degradation in deep space. So going out into deep space, we want to see how humans react and how they change and how they adapt, and we want to be able to study that. And then we also want to look into radiation. Currently, we can study radiation, but we have limited factors being in an Earth-protective environment. So going outside of that, we can look at new environments that we won't be able to study here. So our motivation and as a team, we came together and we looked at many different factors. Our primary science objective and our primary science target was to choose Phobos. This was done for a variety of reasons, one of them being is that it is the bigger moon. It offers more surface area. It offers more chances to find different things. You have a plethora of crater composition on here, so both number and size, mainly given by Stickney crater. We also have a density of Phobos that sort of suggests that there could be water on there. It is definitely a possibility that we want to look into. You also have this streaking from Stickney crater, the white streaking, that could be exposed bedrock. It could be a good place to land. And also you have a better chance of having Mars debris on there, so impacts from Mars that could possibly be on Phobos but not Deimos because Phobos is a closer target to Mars. So our mission overview, for the ASOF mission, it's divided into two primary phases. We have the Precursor phase, which is aimed to provide data on the topography and composition of Phobos and Deimos to assist in planning and technological development for the main mission, the crew mission. The primary phase, in which the crew will travel to the Martian system to conduct their exploration and sample retrieval tasks. So those are our two main phases we have. Now, our Precursor goals are: can humans land safely on Phobos or Deimos if we choose Deimos as an alternative target? So what we want to do is do remote observations, in situ, and impactor. This will give us density and sort of surface composition to see if an EVA is even possible. We don't have final estimates as to whether or not that is true. We also want to have a precursor mission to set up communication system for our main mission. We have the MRO in place, but they do have limited lifespans. Maybe MRO will no longer be in place there. So we would like to have something that's set up to where we can assure that we can communicate with our astronauts. We also want to accomplish some of our primary mission objectives beforehand, because if we can do this, and it turns out maybe we can't do an EVA on Phobos, we can already have these primary mission objectives completed before we even launch our crew to Phobos. And so, because our precursor mission is such an important part of our mission plan, we decided to include a bat chart and go into a little bit more detail about it. So we have our Falcon 9 rocket here, and what we plan on doing is an electric propulsion system. So the Falcon 9 will send it into a Earth orbit, and we'll use a spiral trajectory using electric propulsion to get our precursor mission there. Once it reaches the transitional Mars orbit, we can begin doing mapping of Phobos and Deimos by going into a closer Phobos orbit. Now, we have what we call the Phobos Explorer and the Deimos Explorer on our main precursor mission package. What we would like to do is have the DPS, or the Deimos Phobos scanner, go into a Phobos orbit and drop off this Phobos Explorer. The Phobos Explorer will land on the Martian moon and apply impactor and seismometer data that we cannot do from the orbit. And while we're doing these tests, we want the DPS to be in place to photograph and take different spectroscopy of the unit while we're doing that. The reason we have a Deimos Explorer in place is what happens if the Phobos Explorer fails. The Deimos Explorer will give us a backup, since Phobos is our primary target, we can use the Deimos Explorer to do secondary science if the Phobos Explorer does not give us good enough results. Now, should the Phobos Explorer work primarily, we want to send our DPS package off to Deimos, do science on Deimos, so that way we can study the whole planetary body as a whole. Now, once the science on Deimos is complete, we will leave our DPS there, and it'll travel in a Deimos orbit to help set up that communication network we were talking about earlier. And so this is just a layout of our precursor mission. We have the robotic survey mission to Phobos and Deimos, uses a Falcon 9 rocket. It'll launch in 2026. Our primary crew launch date is 2033. So we expect a 2-year trajectory to the Martian system, and that should give us 5 years of good science so we can adequately prepare for our crew mission. The components are the Phobos Deimos Surveyor, the Phobos Explorer, and the Deimos Explorer. All right, and one of the instrument payloads we're going to include on this precursor mission are listed as followed. We want to mainly focus on soil properties, strength, chemistry, mineralogy, and we have a plethora of science payloads that can do that. Then we want to go into topography and spin rate profile, so we'll use LiDAR for that. Water abundance with penetrator and seismometers, and this will really help because we can now land this Phobos Explorer on Phobos and give us accurate data of the surface. Then we want to study the magnetic field. We don't know if there is one. We don't expect there to be one, but it'd be something interesting if there was one. And then the flux of interplanetary material.
Now, you've heard about the precursor mission down here, but I'd like to introduce you to essentially the other half of the family, which is significantly more trouble. We have the Deep Space Habitat, which houses our crew for the duration, the Orion multi-purpose crew vehicle, our space exploration vehicle, in which we explore Phobos, and our propulsion tank. Now, this happy little fellow over here is the nuclear thermal rocket, which we'll go into a little bit more detail. The rocket was chosen to be a nuclear version option because we experienced significant mass savings over cryogenic stages. Now, here you'll see the bat chart of the program. You can see this. I'm not blocking you. Yeah. Okay, so here you see our launch schedule. Now we have 2 Falcon Heavy stages here to bring the nuclear engines up. We have 7 of these Falcon Heavy lift missions. And you see the customized flange on the top. It's cool. From that, we can take another Delta Heavy and lift our Deep Space Habitat. Now that forms essentially the supply stage, so that can launch, and then when we're ready, absolutely ready, we send up our crew taxi with their SEV to dock and begin our transit. En route, obviously, we expend our first stage propellant and arrive in our parking orbit with our mothership. From that position, we establish our base of our base of operations, and we deploy our SEV to the Martian surface. I won't go too much into that because you'll hear about that later. Once we've completed our scientific experiments, we will return our astronauts safely to the mothership, and we will actually leave the SEV in place as a future exploration vehicle. As we leave, we actually anticipate to be able to control this vehicle telerobotically for some time before, obviously, the lag becomes too much. We then depart, come back to Earth, and everybody is happy there. We bring back our biological and our geological experiments in the crew capsule with the crew.
All right, who wants to go to Mars? 1, 2, 3, 121. All of you want to come? Great. Come with me to the mothership. Oh, wait, actually, I bet some of you are pretty nervous. I mean, we will be 93 million miles from Earth. Everything you know will be so far behind. But trust me, we have your safety as our highest priority. And there are many things that were considered for your safety. Like, for example, radiation exposure. Our spacecraft, our mothership, has so much shielding, but trust me, your money is not wasted. Every ounce of shielding is needed, is essential. Bone mass loss. We have mandatory jazzercise classes to prevent bone mass and muscle mass. Solar cycle. Cosmic galactic rays are a problem. Our galactic cosmic rays are a problem. So flying during the solar maximum prevents the exposure to these high energy particles. A large launch window. Everyone's familiar with delays with flights. With a launch window of 25 days, we can have a weather delay and launch within the next 2 or 3 days and return on the exact same date. Earth line of sight. That means in transit to and from Mars, you'll have access to the Earth. So you can text, Twitter, email, and keep in contact with all of your family and friends. So for this trip, you're going to need to leave your road and your world maps behind. You need a space map. So we'll start from point 1, which is the Earth, on April 7th, 2033. We will perform a Type 1 maneuver to Mars for a 30-day stay, arriving on October 12th. After 30 days, we will depart and return to Earth on July the 6th, 2034. All right, so hop on, get ready. We're leaving Earth now. We're going to take off at 21 miles per second. Just mind-blowing. So we'll come in with this trajectory right here. As we approach Mars, we'll perform a delta V to perform a Mars orbit insertion. All right, ladies and gentlemen, this is your time to relax. We can be here for anywhere up to a week because we have to wait for Phobos to become 180 degrees out of phase with our orbit. What's that, Captain? Oh, it's 180 degrees out of phase now? All right, sorry folks, no relaxing, we've got to go. So now we'll perform another delta V, and this is crazy. We're about to perform a bielliptic Hohmann transfer with an apse line rotation of 56 degrees and a periapse raise of 9,000 kilometers. Whoa, this is going to be crazy. So we're propagating this orbit, and what do you know? We're seeing Phobos, and we meet. So now we just take a little hop over to Phobos orbit, and we're going to trail Phobos for 17 days because we actually made up time by not having to wait in orbit. So now instead of our nominal value of 14 days of science, we can get 17 days of science. There's so much more science that can be done. And this is the best part. This is where you can go out with your families and perform and get in these space exploration vehicles and just explore to your heart's desire of Phobos' surface. There's so much to discover. We'll be in this orbit for 17 days, and sorry folks, we gotta head back home, we gotta pack up. Gotta stow your personal items under your seat and put up your food tray so we can head off. We'll perform another delta V to prepare for an escape trajectory, performing one more, and then our actual escape trajectory occurs at point 7, sending us back towards Earth. And when we return to Earth, we'll actually be going 10 miles per second for reentry. But there's no worry. This system has been designed by some of the top engineers in the world, and we can guarantee you we'll make it back safely. Yes. So you must wonder, how do we get this mothership into low Earth orbit? This thing's huge. Well, first off, we had to run some trait studies between choosing should we launch from low Earth orbit or high Earth orbit. One requires less of a delta V to escape, but getting mass up to a higher altitude is very difficult. Cryo propulsion as opposed to nuclear thermal propulsion. Those provide really interesting trade-offs, and depending on your mass, sometimes the cryo systems are very inefficient due to large mass fractions. And then operations at Phobos. Do we carry the entire mothership around with us and keep the space exploration vehicle attached, or do we detach from the mothership and perform science with the space exploration vehicle? So we went through a detailed design of the nuclear thermal propulsion system to perform sizing studies. And we actually found that in order to use the nuclear thermal propulsion system, you have to increase the fairing size in order to account for the additional propellant volume needed due to the lack in density. So our final decision was to choose the Falcon Heavy. It outperformed the Space Launch System and the Atlas V and the Falcon Heavy in almost most categories, especially in the cost range. And then the Falcon Heavy has the lifting capabilities we need to get all modules up to space to form the mothership.
So Bakari just gave you a great overview of our journey around the solar system, or the inner solar system. I'll be talking about your accommodations during that trip. So we have, as we previously described, a deep space habitat, and what we've chosen is one derived from the ISS to maximize the learning over the 20-year to 30-year program that the ISS will be. So if you notice here, it consists of an MPLM, which was a multi-purpose logistics module. It's connected by a tunnel to one of the nodes. The SAV is another vehicle, which I'll discuss briefly in the next slide, which docks to the node, which allows crew transit. And the MPCV, which is your re-entry vehicle and also the vehicle in which your crew launches in, also connects to the node and allows transit between there, and also transfer of your valuable science payload. So this deep space hab was sized for 460 days based on our long road trip through the inner solar system. Because of this long duration, we've gone with a closed loop environmental control and life support system. We've chosen an atmosphere for it, equivalent to what we experience here on Earth and also what is currently operating on board the ISS, and some special features of it I've described here. We use an ISS-derived structure and really leverage that learning. Also, in addition to having just this closed-loop ecosystem, it's sort of a hybridized architecture that we've gone to, where we use advanced technology that we anticipate will be developed based on current research and proposals for future ECLIS experiments on board the ISS. So these include Bosch reactors, vapor-phase catalytic ammonia removal systems, and ANITA-2. So ANITA, which is an air monitoring system, is actually currently on board the station. This is the next generation version of it. So it's a hybridized combination between these advanced technologies and also what we call the water wall concept. So this is currently on a NIAC proposal, where you have these polyethylene bags lined up all around your capsule. So these provide two main functions. So they do life support functions, so that it could be air revitalization, trace contaminant control and removal. It can process grey water. And simultaneously, it also acts as radiation shielding. So as you've heard throughout the week and in the previous team's presentation, shielding against galactic cosmic rays is one of those barriers that we must overcome to keep our crew happy and healthy. In addition to this shielding, we also propose using a heat melt compactor as our waste management strategy. So what this is you get your packaging plastics and materials and your food wrappers, you stick it in a big machine, oh, it's not that big, sorry, it's a small machine. And then it compresses it with heat, and then you get these waste pucks. And so you can use your wastes and supplement your radiation shielding in your habitat. In terms of the space exploration vehicle, Based on the mission profile that Bakari presented to you, we've sized it for 30 days, so that gives you a little extra time to move between Phobos and your Martian orbit, where the rest of your habitat stack is located. We've sized it for 2 crew with 8 nominal science EVAs and plus 2 contingency EVAs. Because of this duration, this shorter duration of 30 days, we've chosen an open-loop life support system. And the reason why we've gone with that is because we want to maximize reliability of the system. You've got less moving parts when you've got an open-loop ecosystem. A more closed-loop one would be more mass efficient, but it would be less reliable. And one of the main rules of thumb that we've been using throughout this entire mission architecting exercise is crew safety is king. The atmosphere we chose in here is slightly different from the deep space habitat atmosphere. It's 70.3 kilopascals, 26.5% oxygen. This allows you to do basically a no pre-breathe EVA if you choose this next generation spacesuit called the Mark III here. So traditionally on station, astronauts have to do 4 hours of pre-breathing to denitrogenate their system to prevent the bends from occurring. If you have to do that while you're out at Phobos, you're losing a lot of mission time. So clearly you want to do quick EVAs, and this is facilitated by these suit ports, which are located here. So you see this crew member here, he opens this hatch, jumps into the back of his spacesuit, which is just hanging off there. The hatch closes and he's out and he's ready to go. In addition to that, we're also leveraging commonality between the SEV and the spacesuit that we choose. So we actually share the oxygen and water amongst the two within the same tanks on board the SEV. Also, we're using lithium hydroxide canisters for CO2 removal on the SEV, which is also compatible with the portable life support system on the spacesuit. So for example, if your spacesuit's lithium hydroxide canister didn't work, you could get one of your spares which you brought, maybe budgeting for the SEV, and you can place that on there. So you've got a lot more flexibility there, and that reduces your spares mass. In addition, same concept with our activated carbon for contaminant control. So this comes in little cartridges that are compatible with both systems. And in terms of ventilation, you can also use a common fan that powers a ventilation circuit on the portable life support system, as well as the SEV. So you've got a lot of areas of commonality there. In addition, we're going to be using a similar concept to what we described earlier with these water walls. All our waste products, so our metabolic waste, our urine, our feces, will be stored in bags located along the wall of your spacecraft. Again, for radiation shielding purposes, not because we like to paint with metabolic waste. So, in terms of human factors and crew health, so clearly we need to keep our crew healthy, happy and alive throughout the mission in order to complete mission objectives. In terms of crew size and selection, we've chosen a 3-person crew with an age range preferably between 40 and 55 years. And this number is bounded by the physiological limits on both ends of those spectrums. In terms of skill distribution, they'll need extensive training in a variety of areas, including geology, maintenance and engineering, and medical event management. If you look at the habitable volume of our spaces, it's about 25.5 cubic meters per person, which is a pretty good number when you consider crew psychology effects. Also, in terms of our habitable volume distribution, there are zoning areas throughout the habitat where you have your private personal space, so your sleeping quarters, and then your group social spaces, such as your galley. In terms of crew healthcare, our crew healthcare protocols cover factors such as crew health monitoring, biomedical measures, and psychological countermeasures. Also, because we baseline our deep space habitat on ISS infrastructure, we can use existing infrastructure such as the ISS medical kits that are currently flying. They integrate seamlessly into our deep space habitat. That also includes life support technologies that are proposed for future experiments. So we can leverage the learning that we obtain from life support technologies on the ISS over the next coming years and basically plug and play and upgrade to your new requirements for your Martian mission and plug them into your deep space hub.
All right, so the science is driving much of this mission, and I want to step back and remind you, recap, that the Precursor mission, I can't overstate the importance of it. So there are two images here, a photograph of Phobos and then a topographic elevation profile with a color ramp. And the big X's that you see, site A, B, C, and D, those are all impact sites that start at the Precursor level. And just to remind you, there's a Phobos Explorer Pack and a Deimos Explorer Pack. Each of those can deploy 4 impactors. And these are essentially modified projectiles with a mass in the front that's driven by a small amount of propellant. And in the nose of these, there will be an accelerometer, a thermocouple, and some instrumentation that will give us a sense for the soil properties, the regolith properties. There will also be sort of an ulterior, brutish motive of just digging up as much dirt as we can upon the impact. There's some indication that in some places on these moons, the soil thickness, the regolith thickness may be as much as 100 meters, and certainly those sites would be prohibitive for manned landing, at least with the currently envisioned technology. We are seeking places where the regolith cover is not so thick for a follow-up manned mission. So the impactors would have, or data would begin coming in from the Precursor mission in probably late 2028, and the manned mission the astronauts would not arrive here until sometime during 2034. Depending on the data we receive from the Precursor mission, we have selected Site A and B as our top choices to send our astronauts. A is our top choice because of the dual material that we have, both the reddish material that could be derived from the Martian surface, the bluish radial material that apparently is ejecta from the Stickney crater. This also has an IR spectra indicative of hydroxyl minerals, possibly water, and so we want to collect samples from there. I want to call your attention also over here to the topography. This is a highland rim next to Stickney crater, this is Site A, and based on the elevation profile, we believe that there's a good chance that there is some bedrock, or at least a very thin covered regolith that can be found in this area. If for some reason those sites prove to be prohibitive, we would then consider sites C or D for the follow-up manned mission. And what we envision upon astronaut landing is roughly 14 days in which to collect samples and do experiments. The principal sampling will be for rocks and soil. We have planned 30 samples, 15 from each of 2 sites, and 12 soil samples from 6 from each of the 2 sites. The total mass, or at least Earth mass, for these samples upon return is approximately 250 kilograms. We would also, like a secondary goal, would be to do some core drilling. We propose 3-meter deep handheld drill holes. This is technology. This particular image comes from the Apollo 15 mission. This was attempted on 3 Apollo missions and accomplished on 2. And so it is demonstrated space technology. We will plan to deploy passive source seismometers at the landing site, and depending on what our tethering constraints are for our lander, we may be able to consider an active seismic source where we would have the source near the spacecraft, deploy a seismic array, and be able to get a third-dimensional look into the body. The final instrument that we would plan to deploy, at least from our planning stage, would be a retroreflector. This is one that was left on our moon by the Apollo 11 mission. This is simply a passive reflector at which you can shine a laser beam. It travels there, it returns, and the return time tells you the distance. And if you monitor that over a long period of time, decades to centuries, you can learn quite a lot about the orbital mechanics of these bodies. And this little device, as simple as it is, has told us wonderful things like our moon is precessing away from us about 3.8 centimeters per year. It has also allowed us to constrain the universal gravitational constant to way out 11 decimal places or something like that. And so it's both inexpensive and easily deployed, and it's highly recommended to be left on Phobos. Looking back at Mars, it would be easy to have a Martian rover, for instance, periodically shine a laser up towards Phobos, collect the data, do that, each week or something like that for a long period of time. Lastly, we have shown a nanosat release here as part of our public outreach part of the mission. We would like to propose that people design something that could be done with nanosats, and we would plan to release them at one or both of our sites.
All right, so now that we know roughly where we want to go on Phobos, and what we want to do when we get there, we need to talk about how we're actually going to do it. So, as you know from earlier, there are 3 crew members, one staying up in the mothership, while 2 descend to the surface in the SEV. These 2 crew members, when the SEV lands at nominally 2 landing sites on Phobos, they will perform a series of 8 EVAs, 4 at each location, rotating which crew member goes out each time. When the SEV lands at a site that's going to be used for exploration, it actually anchors, and the anchoring system, we've explored a wide range of experimental anchoring systems and have determined that we can easily adapt any technology to the SEV as needed upon knowledge of our landing sites after the Precursor mission. You notice that there are 2 different EVA modes. The first mode is kind of our worst case scenario. If we do encounter a situation where we need to land on a very thick, dusty layer of regolith, and by thick I mean over 1 meter thick, fine-grained, smaller than sand dust, up to over 100 meters thick, we need to have a way to do this EVA without interacting with the surface as little as possible. Interaction with a surface of this kind can cause dust kickup and be hazardous to the crew and prevent visibility, etc. In order to do this, the crew on EVA, the crew member will actually have their feet fixed to a robotic arm at the front of the SEV. As you can see in this image, this EVA mode has actually already been tested very successfully on the NEMO's undersea missions on Earth, and it's actually one of the best EVA methods for ease of mobility in a low-gravity environment for manipulating large equipment like a drill. For Mode 2, this comes into play if we have a friendlier, rockier gravel terrain on which our astronaut on EVA can actually exit the vehicle on a tether, which provides a greater range of mobility across the surface compared to this robotic arm. Then they can travel to the location where they want to perform science, leave behind an instrument or collect a sample, and anchor themselves using a personal anchoring system that is a shrunken down version of the anchoring system on the SEV itself. This anchoring system simply makes sure that they don't drift up too far, have difficulty maneuvering while operating something that could range anywhere from a hand crank drill of the Apollo days, or maybe even a power drill if we find that the surface warrants it. Again, depending on what we glean from the Precursor mission. This just makes sure that the astronaut doesn't drift away and can actually operate that equipment successfully.
All right, so what we've learned over the last few slides is that the planetary science payload on mission ASOF is very, very substantial. We're going to get a lot of good data about that. But what we also have to consider is that the primary objectives for the mission include obtaining physiological, psychological, and crew health maintenance data that will perpetuate the ability to send humans back to the Mars system, to go to the surface of Mars for sample return, and potentially to establish permanent human presence on Mars. So we've dedicated a bioscientific payload to the habitat module that we'll be using on the mission. This is composed of two general themes. The first is a NASA-guided scientific suite, and that is our in-flight bioscience instrument suite. That needs to be scaled to at least 2 levels. So 20 years out, we're just starting to propose what these science definitions will be, at least from a bioscientific standpoint, with the degree of technological development and the high rate of development and equipment modifications going on. What we want, essentially, is first a molecular analysis capability. So we're talking about large non-protein molecules and small proteins. So if you've ever seen a newborn, what they do in the first day is to stick their foot and put a little small sample of blood, we're talking extremely low volume, on a sample collection card. We can then run that through mass spectrometry, and we're able to see these sorts of molecules that I'm talking about. Some things like hormones, biomarkers for degradation of human systems, that sort of thing. And that technology is shrinking as we speak, and it's being developed in a way that can see larger and larger protein sizes. So we'll couple that with additional technology, and we'll keep this entire thing contained ultimately to the size of one current ISS scientific rack structure. The second scale we need to be on is ionic, because we need to see things like calcium ions that are leaching out of bones as they degrade. And so that can be done with simple sort of hospital-grade technology that we have now that already has been scaled to smaller equipment sizes, and that will continue to be pushed forward in both the molecular scale and the ionic scale to smaller technology, cheaper, easier, less reagents, that sort of thing, because the primary economy for this sort of science is not the deep space mission to Mars. We have a lot of economic drivers to get our technology into high resolution, low cost, low volume sorts of scenarios. The second thrust of our scientific endeavor will include academic and industrial linkage. So you don't want to just say we're doing NASA-only payloads. What we want to do is something similar to what the ISS does now. You can put out something through CASIS, which is a center that directs International Space Station research, and you put out a request for proposals. So ultimately we get the academic and industrial communities coming in, telling us what the most current, most cutting-edge science is. We review that within a peer review process that takes into account what we want, what we're able to put on these sorts of missions, and what sort of data we need. And ultimately we can put that into the second ISS rack that we have integrated into our habitat module. When we do have biological samples, we will need to preserve them. And we'll also, based on the needs of our geology team, need to preserve all of our samples as well. So that can be done with a 2-part freezer system. We'll need 8 individual modules, 6 for geological samples and 2 for biological samples. And we're planning to implement a modified Melfi system, which is an ISS-proven freezer system that can get you down to minus 80 degrees Celsius. The geology team defined their needs as negative 100 degrees Celsius, so what we're going to have to do is integrate glacier technology, which is the newest sort of freezer they've got to send payloads up to the ISS and bring them back at a stable temperature. So we'll need to integrate that sort of thing, i.e. modified Melfi, to be able to provide Melfi volume with glacier temperatures. So finally, our outcomes will be, number one, to provide mid-mission countermeasure customization. So when we talk to NASA scientists about what exactly we ought to include in a bioscience payload, they said, we don't just need you to bring a bunch of samples back. And that's sensible. We don't have enough room in our crew module to put tons of samples stacked everywhere and bring all that back. So they'd much rather have in situ analyses. You have a problem or just at regular intervals, we take a look at what's happening with these people, and if we need to make behavioral or pharmacological changes in the astronaut health regimen, that can be done, and we can establish a higher degree of performance for our astronauts during the entirety of the mission. The second outcome is to provide a more extensive repository for deep space exploration health data, so we can move beyond what will be the next 20 years or so of ISS-based research into a deep space model where we're able to more accurately predict what happens when you're going as far out as the Mars system. You have unique factors like radiation that are going to give you problems. The second theme that I have to share with you today is something that my engineering colleagues have described to me as a showstopper, and that is the fact that when we checked with NASA's Office of Planetary Protection, Team Voyager found out that when you contact the surface of Phobos, we're going to have what's called a restricted return, which means that we essentially have to treat any material on Phobos, which potentially has been accreted from Mars and could be harboring sort of entombed microbes, which could be pathogenic to humans. We're going to have to treat those surface samples on Phobos like you would treat a pound of the plague or a sample of Ebola virus or something. And that means we're going to have a very, very specific architecture to get these samples back in full containment and reliable containment, even with mission failure, to the Earth without exposing our astronauts or the people back on the planet. Because ultimately, we rely on international collaboration to operate one of these sort of super exploration class missions. And so if we tell people, oh, well, we're going to go unilaterally and we'll just bring it back and hope everybody's okay, we risk the chance of losing international support. So ultimately, the question then is, how do we avoid this phenomenon called back contamination, which is bringing some bits of Mars with pathogens back to Earth and killing us all? That's done by breaking the chain, which is an engineering mechanism we have to do. We need to do a little bit of development. We found out about these planetary protection problems late in our design phase. So the issue was, in 24 hours, how do we solve this problem from an engineering standpoint and integrate it into our habitat module and make this work in a way that will allow JPL and headquarters to take a look at this mission and say not only will we accept it, but we'll be able to fund it and it won't kill our international support. So you break the chain by using a JPL-proven method of sterilization. What we do, say you're at the surface of Phobos, you have your sample, you process it a bit, and then ultimately it ends up in a primary containment chamber, which is, say, a box of some sort of metallic material. We then take that back on a science exploration vehicle to the deep space habitat, which has a built-in airlock. Now this is a payload-only, or a sample-only airlock that we move our primary sample containment units through, and it employs a vapor phase hydrogen peroxide sterilization system. This allows us to kill off any potential microbes, any life forms that would be on the surfaces of these, because you've been in contact, and we have Phobos material moving around the environment during sample collection outside in vacuum. So we have to get rid of that. We do that inside the airlock. We then open the interior to expose the habitat. We have an astronaut inside the habitat, remove that, take it to the freezer. The freezer the Melfi freezer we talked about, provides secondary containment. We lock that in. Now, the important thing to note is that when we're coming back, even in the event of a total mission failure, we have to bring these samples back through reentry and through impact with Earth without losing containment, which is a marvelous engineering challenge. So we'll do that with freezer containers that are large enough to undergo those sorts of strains. And ultimately, what we'll do is facilitate the progression of our mission from just the design phase to a fundable phase, where we won't end up risking bringing back dangerous pathogens to the Earth.
You might have noticed by now that Team Voyager is really excited about this mission. But for this mission to be a real success, we also want the public to be excited about this mission. So we came up with a few things for public outreach. First, we've allocated more than 1.25 tons for public outreach payload. These will be distributed on the Precursor mission, on the Phobos Explorer and the Deimos Explorer, but also on our human mission. So we will have competitions, maybe at universities, also for commercial spaceflight companies, to come up with ideas, with experiments that we can send up to the Martian moons. So I think this is a really great possibility to involve also students, to have them design something that the astronauts will release on Phobos. But we don't want to just stay and do outreach for people who are already kind of excited about space. We also want to reach people who are not interested in space yet. So we'll probably use the internet a lot, using Facebook and Twitter, have the astronauts post status updates. How's it going in the deep space habitat? How is the food today? We'll also have educational interaction with K-12 programs. We can have the school kids send emails to the astronauts. The astronauts going to answer back. We also might have some pre-recorded video broadcasting over NASA TV. So we got the public excited.
Now we're getting the whole world excited by also involving international collaboration. These are going to be mutually beneficial. There are financial benefits. We don't have to carry all the costs. We can split the costs, but there are also scientific benefits. We can benefit from the the knowledge and experience of the involved nations. Also, multiple launch sites around the globe will allow for contingencies. We can just launch from another site, and also launching the rockets from sites from all over the world will impact more people globally as when they see those rockets going up, they're just going to be excited about it.
So why have you listened to all of this? Is it a love of my soft, sultry voice? Probably not. It's because you want this. Men and women on the surface of an asteroid, hundreds of millions of kilometers from where they were born. And we can do this. These kind of missions facilitate exploration deeper into the universe. They facilitate other programs like the NEO program, where we have astronauts sent to near-Earth objects. These are very similar in operation to what we're proposing here. You further your knowledge of humans habitating in space for long periods of time. You have potential for in-situ resource utilization. This is a big key. You saw we had 11 launches to get this fuel up into space, and that's a lot. It's very energy intensive. What if you could harvest some of that fuel from your station? You could essentially create these fuel points throughout the solar system. And nothing we've put forward here is impossible. It will take time, sure, but nuclear propulsion, it can be done. International collaboration, we can launch from Florida, from Texas, from France, all these equatorial sites that can get our units up into space quickly. I should have mentioned before that we have a lot of launches. The time between flights, the turnover, can be as much as 88, 120 days. To try and launch all of that from a single position, it's very difficult. So we need that collaboration, we need this technology development. But through this, we can achieve these kinds of missions. With that, I'd like to thank you for your attention. I'd also like to thank our mentors, our organisers, Nick and Jason, everyone who's spoken to us and helped us out during this week. I'd like you now to direct your questions, please, to the podium, and thank you for listening.
Yeah, why doesn't the rest of Voyager come up? We have time for some questions. Nigel?
Did you have fun?
Yes.
Lee?
What is your mission name stand for?
It is the discoverer of the 2 moons of Mars.
Oh, nice.
Julie?
So it was not clear to me, and because I'm not an engineer, what were the drivers that led to the 11 launches?
We'll go ahead and direct that to Paul.
All right, so the launch mass itself might be not bigger than, for example, for Team Explorer, but we chose a launcher with a smaller launch capacity. And that's basically, if we launch with the SLS, we also arrive at 6 launches in total.
But as you might have seen in the table, the cost for doing 11 launches is about a third of the cost for doing 6 launches with the SLS. So the cost really goes down. Even though it sounds complicated to use 11 launches, but it's a 66% reduction in cost. So that's like that. Right.
David?
Continuing on, I guess, with the launch vehicles, you mentioned towards the end about having international cooperation, make use of international launch sites. Did you have international launch vehicles, like the actual launch vehicles that exist today, in mind, and how you would break down the vehicles in order to fit on those launch vehicles?
guess it's again me. So we looked into different options that are being developed. Unfortunately, we couldn't find much information on, for example, on the Russian development of the Angara 7 launch vehicle. So I guess that would be something which would require further investigation. But yeah, so far the Falcon Heavy and the SLS, maybe the Atlas V heavy lift version, which are basically the only options. Maybe with the Ariane 5 ME development, maybe this would be an option later in the future.
Any more questions? Oh.
Given the other things you're doing, why were you constrained? Why did you feel constrained to existing launch vehicles?
I mean, the launch vehicles we're using right now are not existing. They are in development. And so going further than from vehicles which are in development, we can't really assume or develop by ourselves a completely new launch vehicle. So, yeah.
So if I can add to that, because safety is a big concern, we want to make sure that all the technology we're using is safe and proven on previous missions. So we cannot rely on something that is not even in design phase.
David.
For your Precursor mission, you had a set sprite point down to Phobos first and then back up to Deimos. Did you consider going the other way around, and why did you choose that sequence?
We chose to go to Phobos first because that's our primary EVA target, so it has to be our primary goal. If the package going to Phobos were to fail, we would still have the Deimos package that could be used on Phobos. So it was sort of to set up safety precautions in case we could not complete EVA Precursor.
Did you think that there would be additional risk of stopping by Deimos first?
No, there isn't an additional risk by stopping by Deimos first, but if we were to launch our package to Deimos first, and that one were to fail, then we could it would lessen the chance that the one on Phobos were to work. So we wanted to increase the likelihood that we could get the best data from Phobos.
Dan?
Yeah, I was just going to ask you guys what your strategy was for a departure window and take into account the complexity of doing this mission with multiple launches, and how do you handle that?
Well, one of the main tools we used was Lambert solver, just to get initial ideas on what the actual orbits were that we could complete. And then we looked at planet phasing to see, for the Precursor, would a Hohmann transfer be the most efficient? So there are certain launch windows associated with that, but since we can perform a different type of orbit where we don't precess 180 degrees in the heliocentric orbit, then from that we could establish when our launch windows are, and then use that information to assess how the delta V changes as the launch window, as you progress through the launch window, and how long the wait time is at the planet. And really the main driver for that was Eclipse essentially said that they didn't want the astronauts to be exposed to the space environment for more than 30 days. So that's why the launch windows were set as such.
So, adding to that, we actually designed the propulsion modules to the worst case scenario if we would have to, for example, to mitigate a launch failure. So we basically, April was our first starting point, and then one of the last one was in May. So we designed basically propulsion modules for the worst case, which will be starting in May, and then basically catching up with the mission timeline.
Right, for a single departure window, though. April to May.
Yes.
A question I was going to ask the previous team, but since you have 3 rather than 4 crew members, that's perhaps more appropriate for you guys. Have you considered what if you lost one of the crew members during the mission? Would you still be able to continue the mission completely? Either,
I suppose it depends on which phase of the mission you were in. If worst case scenario, you lost a crew member out on EVA and the secondary crew member was not able to recover them through the secondary support, then that would be a definite source of mission end, probably a source of mission failure. Actually, one of our reasons for leaving the SEV behind is so that we can test use of it as a telerobot on Phobos. So if we were to lose a crew member and still wanted to, and had collected no samples and still wanted to get science data out even after that loss, we could have the third crew member in Phobos orbit teleoperate the SEV and still have the second crew member in the SEV do a spacewalk in the either their spacesuit or the backup spacesuit and complete some level of the mission.
And you would be able to bring the remaining crew members back on?
Yes.
One more question?
Did you, in the science objectives, you talked about geology and biology, did you have Mars objectives?
So the Mars objectives are something we didn't quite focus as much on because we wanted to open that up to the public outreach aspect of our mission. That is primarily why we allocated so much space, is so that way universities and other corporations could use their time to focus on Mars study.
So the Mars objectives in this mission are primarily technology demonstrators. For instance, we said that we're going to leave the SCV back at Phobos, so that gives you a technology demonstration for teleoperation, for instance. The other thing that we are doing, which will serve in terms as a Mars aim, is to study the physiology and the psychology of the astronauts being out on the mission for so long. So I think that's extremely critical for a Mars mission. So a lot of I think as one of the advantages of going to a Martian moon is that you get to do a lot of things that double up as which are actually Phobos-centered objectives, but also double up as Mars objectives, because you will end up using or being exposed to the same kind of situation when you go to Mars. So by default, it sort of becomes a Mars objective as well.
Could I add to that? So indirectly, we will learn something about Martian history at least, because if we can constrain the origin and the composition and age of these moons, that will tell us something as well about the planet Mars. If it turns out that they're simply captured asteroids, maybe that's less, but if it turns out that it's ejected from the surface or some sort of early bombardment impact origin as for our own moon, then that does indirectly tell us more about Mars.
Okay, folks, let's thank Voyager for their efforts.